Hi, welcome to another chemistry video. Today we're going to talk about kinetic molecular theory and deviations from ideal behavior of gases. We're going to explain the relationship between the motion of particles and the macroscopic properties we observe of gases. We're going to do so in terms of kinetic molecular theory, or KMT theory as I'm going to refer to it. KMT theory is a particulate model, and we've already began looking at graphical representations of gases by plotting pressure, volume, and temperature, and we'll do a little bit more exploration in terms of particle speed. Just a reminder that pressure is the force exerted when a gas particle collides with the wall of a container. So as gas particles collide with the walls of a container, we get pressure readings, which can be in several different units. Atmospheres, millimeters of mercury, and torr are the most common, and you're going to have to be able to convert between those three units. So please write these units down and these conversion factors down if you don't know them already. We're going to do the following practice problem. So please convert 657 millimeters of mercury to atmospheres and 830 torr to atmospheres. I'm going to pause the video. Now let's take a look at these conversions. So at the very top, I've written the conversion factors. 1 atmosphere equals 760 millimeters of mercury, which equals 760 torr. For the first question, 657 millimeters of mercury to atmospheres, we start with 657 millimeters of mercury. We divide by 760 millimeters of mercury to cancel out our units. We're left with 1 atmosphere on top, and we get 0.864 atmospheres as our answer. For number 2, we have 830 torr, which we're converting to atmospheres. We start with 830 torr, cancel out torr, and for every 760 torr, we have 1 atmosphere, which results in 1.09 atmospheres. The reason we're focusing on converting to atmospheres is because most of the time for the ideal gas law, you're going to need your pressures in terms of atmospheres. Now let's talk about kinetic molecular theory. There's 5 postulates that you need to know. The first postulate is gases are composed of tiny particles, atoms or molecules, whose size is negligible compared to the average distance between them. What this means is that the volume or size of the actual individual particle is insignificant compared to the volume of the container, meaning our particles are far enough apart that their size does not matter. This also means that the gas is going to fill the container completely and fill up all the empty space possible. Gas particles move in random straight lines in all directions at various speeds. So let's break this down a little bit. This means that if a gas particle collides with another gas particle or with the wall of a container, it's going to bounce in a straight line motion. Additionally, it's going to move in any direction at various speeds. So when we're talking about, for example, temperature, we talk about average kinetic energy. What this means is that there's some particles that are moving really, really fast and some particles that are moving really, really slow. So there's a wide range of particle motion that gets to that average. The forces of attraction or repulsion between our 2 gas particles is negligible. What this means is that intermolecular forces are theoretically not affecting our gas particle behavior. When gas particles collide, the collisions are elastic. Elastic collisions mean that there's no kinetic energy lost between the particles or the particle in the wall of the container. Elastic collisions is consistent with the observations that we make about gases. When gases are left just in a container, we do not see a loss in energy, meaning the temperature remains constant. Our particles are not losing energy, because if they lose enough energy, they would convert to a liquid. And we don't see spontaneous gases just changing into liquids. Normally, that requires a significant temperature change. Our fifth postulate is that the average kinetic energy of a gas particle is proportional to the Kelvin temperature. This means that all calculations involving gases have to be carried out in Kelvin. So if you are given information in degrees Celsius, you have to convert to Kelvin using K equals degrees Celsius plus 273. In addition to using Kelvin, it is beneficial for us because this means we don't end up getting negative volumes, which don't exist, and we don't get negative pressure or negative temperature values. So everything's going to be carried out in Kelvin, and normally your pressures are going to be carried out in atmospheres. Now let's look at some non-ideal behaviors of gases and explain the relationship between that non-ideal behavior, interparticle forces, and the volume. So kinetic molecular theory is for ideal gases, so under the best circumstances possible. But there's limitations to ideal gases and ideal gas conditions. Real gases do have particles that are attracted to one another. We have proof of that. Most gases probably fall into a polar molecule category, which means they will be attracted to each other. If they weren't attracted to each other and those particles would never stick to each other, you would never be able to condense a gas to a liquid. We know that's not true, which means there has to be some sort of force of attraction between those gas particles. We assume ideal conditions in order to use our equations like the ideal gas law. Additionally, pressure and temperature are going to have a huge effect on how our gases are behaving. At high pressure and low temperatures, gas particles come really close together and make two of the postulates of Kmt invalid. So high pressure and low temperature are really non-ideal conditions for gases. When gases are pressurized into a small amount of space, the gas particle size does become significant. As we condense that space smaller and smaller, and our gases are pushed together via pressure, you end up with your gas particles pretty close together, which is not ideal. Low temperature means less energy, so particles are going to become more attracted to one another. Overall, their energy is decreasing, the particles are slowing down, and the forces of attraction between our particles are more likely to act upon each of those particles. Under these conditions of high pressure and low temperature, gases behave unideally or like a real gas, and this is going to have consequences. Again, the size of the gas particles are no longer negligible. The actual pressure of the gas is usually lower than what one would expect when assuming no attractive forces between the particles. In real gases, particles are attracted to each other, so they end up colliding against the walls of the container with less force and less pressure than you would expect, because there is now an attractive force between our particles, pulling those particles away from the sides of the container. If you have any questions, please let me know. Otherwise, we'll be discussing this tomorrow in class. Have a good night.